Hello students, so this is our lecture 16 of our subject digital system design, and the topic which we are going to cover today is flip-flop characteristics and their asynchronous inputs. So let's start with the contents. So these are the contents which we are going to cover today: characteristics of flip-flop, flip-flop with asynchronous inputs, then what are the different operating characteristics of flip-flops, and this point both are different. And the first one, we will be calculating an expression, a mathematical expression kind of thing, which will be describing the flip-flops behavior. Okay. And the third one is a kind of theoretical characteristics of flip-flop, or we can say the real time performance based, the characteristics which affect the performance of the flip-flops, those characteristics. And the last topic which we will be covering is the difference between the asynchronous and synchronous circuits, which will be making the basis of the topics which we are going to cover in the next lecture. So let's start with the first topic. So characteristic equation of flip-flops, and we have already covered in our last lecture. There are 4 flip-flops. First one is the SR flip-flop, then SR was having some deficiency in one of the case. So for that we designed a JK flip-flop, and then SR JK. The special cases from these SR and JK were obtained as T flip-flop and D flip-flop. So these are the 4 flip-flops which we had already covered in our last lecture, and today we will be designing the expression for their outputs. Like the expression for an AND gate is y is equal to A dot B. Expression for OR gate is y is equal to A plus B. Similarly, what will be the expression for this SR flip-flops Q, okay, in terms of the independent variables? The independent variables are S, R, and this is well known to us that these are sequential circuits in which the output is also dependent on the previous outputs. So that means S R Q N is the previous output, okay, and this Q n plus 1 is my next output, okay. So depending on the values of the input and the previous output, we will be finding the next output, okay. So for S R Q n, 3 variables are there. So we have mentioned 8 cases from 000 to 111, okay. This we can see that we have covered all possible cases for SR. Now SR's truth table is also known to us, which says that for 00 there will be no change in the output, for 01 output will be 0, for 10 output will be 1, and 11 is considered invalid. So we are using that same thing in the first case, or we can club these cases as well: 00, 01, 10, 11, okay. So when S and R are 0, then there is no change in the output. That means whatever the previous value was, it will remain same for the next output as well. That means 0 will remain 0, 1 will remain 1, and for 01, whatever the previous value was, the next output is going to be 0. Similarly, for 10, whatever the previous value was, whether it is 0 or 1, the next output will be 1. In the previous case it was 0, and in this case we can mention it as Q n. And the last 2 cases, for S is equal to 1, R is equal to 1, it is known that for S1, R1 output is invalid. So I have put a cross there for last 2 cases. So this is the operation table, or we can say characteristic table of the SR flip-flop. Now from this characteristic table we can see that this Q n is having 3 ones and 2 don't care terms. So the location of these 3 can be considered 001 corresponds to 1, this is 100, that means 4, this is 101, that means 5, and the last 2 don't care terms are 6 and 7, okay. So 1, 4, 5, 6 and 7. So these 1, 4, 5 are the min terms and 6, 7 are the don't care terms, okay. This is not min term, this is don't care term. So we have to prepare a K map for S, it will be S will be on the row side and R and Q n will be on the column side, okay. So S can have value 0 and 1, R and Q n can have 4 set of values 0, 0, 0, 1, 1, 1 and 1, 0. Then putting these min terms and don't care terms in this K map, 1, 4 and 5 and 6 and 7 are the don't care terms. So, if we prepare the grouping in this K map, then we can see that this is a quad and this is a pair. Okay. So, this quad corresponds to, this one is common which corresponds to S, and from the row side there is nothing common. So, we can say that it results in S only, and from this pair we can see that there is nothing common from the row side, and this 0 1 corresponds to R bar Q n. Okay. So, S plus R bar Q n, this becomes the characteristic equation of the SR flip flop. Q n plus 1 of SR flip flop is equal to S plus R bar Q n. Okay. So, this is the characteristic equation of SR flip flop. Similarly, we can derive characteristic equation for other flip flops. Let us continue with that. So, this is a JK flip flop now. The only difference between the characteristic table of a SR flip flop and a JK flip flop is that the last two cases are not invalid. Okay. So, that is why there are don't cares are not there, and proper binary values 1 or 0 are present there. So, in the same way we can understand that table for 0 0, 0 1, 1 0 and 1 1. For 0 0 we know that there is no change in the output, 0 remains 0, 1 remains 1. For 0 1 output is 0 whether the previous value was 0 or 1. Similarly, for 1 0 the next output is 1. Okay. So, we have again mentioned them here, and for 1 1 the output is not invalid, it is the complement of the previous output, that means the toggled output. Toggled output means the complement of the previous value, that means 0 becomes 1 and 1 becomes 0. Okay. So, this is the characteristic table for JK flip flop. Again, from this characteristic table we can observe that there are 4 high minterms which correspond to 1, 4, 5 and 6. So, this 1, 4, 5 and 6 are the high minterms for Q n plus 1 of JK flip flop. So, let us mark the independent variables on the K map, then place these minterms 1, 4, 5 and 6. So, the grouping is quite simple, this is a pair and this is a pair at the edges of the bottom row. Okay. So, this will result in 0 1 corresponds to K bar Q n, and this thing corresponds to J from the row side, and from this 0 0 and 1 0 this 0 is common which corresponds to Q n bar. So, it becomes J Q n bar. Okay. So, we can mention it here that Q n plus 1 for JK flip flop is equal to J Q n bar plus K Q n. Okay. So, this becomes the characteristic equation of the JK flip flop. Now, let us proceed with the D and T flip flops. So, these D and T flip flops are derived from the SR and JK only. Okay. So, D flip flop says that whatever is the input, it will be available at the output. So, the characteristic equation of and the characteristic table of the D flip flop becomes very simple. Okay. So, this D is the input and Q n is the previous output, and this Q n plus 1 expression I have to calculate. So, for D is equal to 0 and D is equal to 1, I know that whatever the previous value was, either it is 0 or 1, the next output is going to be 0 because D is 0. Similarly, for D is equal to 1, whatever the previous value was, the next value is going to be 1. That means 0, for 0 input I will be getting a 0 output, for 1 input I will be getting a 1 output. So, we need not to find the minterms and solve anything, it is very much obvious that Q n plus 1 is exactly equal to D. So, instead of finding minterms and then feeding those minterms into the K map, it will also result in the same value. So, we are not solving that K map for that. So, the Q n plus 1 for D flip flop. Okay. So, Qn plus 1 for D flip flop will be equal to D. So, this becomes the characteristic equation of D flip flop. Similarly, we can proceed to the T flip flop. Now, the T flip flop is derived from JK flip flop, which says that if I apply 0 input, I will be observing no change in the output, and if I apply a 1 input on the T terminal, then I will be getting the complemented value of the previous output. Okay, that means the toggle case. So, for T is equal to 0, output remains unchanged. That means, I can say that it is Qn for T is equal to 0. Similarly, for T is equal to 1, output is Qn complement. This can be seen that 0 becomes 1 and 1 becomes 0. Okay. So, this is the characteristic table of T flip flop, and from this T flip flop characteristic table, I can see that this Qn plus 1 is dependent on T and Qn in a very much obvious expression, which is similar to an XOR gate. This 0 1 1 0, this corresponds to an XOR operation. Okay. So, I can simply write it that Qn plus 1 for a T flip flop will be the XOR of T and Qn. Okay. T XOR Qn, or we can write it in the form of expression T bar Qn plus T Qn bar. Okay. So, this becomes a characteristic equation of T flip flop. So, these characteristic equations are very important, and when we will be designing the state machines are the complex sequential circuits in which are designed to perform a specific task. These characteristic equations are going to be used while designing those state machines. Okay. So, with this we come to the end of this topic of characteristic equations, and now let us proceed with the characteristics of the flip flops. So, by characteristics of flip flop we mean that propagation delay time, setup time, hold time, maximum clock frequency, power dissipation and pulse widths. Okay. So, let us cover them one by one. So, propagation delay, it is the time interval of the time required after an input signal has been applied for the resulting output change to occur. That means, I have applied an input to a flip flop, and those inputs will be processed by the flip flop, and then output will be delivered by the flip flop. So, this processing time in which all feedbacks are going through to find the stable output. So, the time between the application of the input and obtaining a stable output is termed as the propagation delay. That means, this time is going to be there always, it cannot be minimized. So, it is going to be the propagation delay. Okay. Then setup time, as the name suggests, it is some kind of time which is required before the actual thing, okay, for setting up something. Okay. So, it is the minimum time interval required for the logic levels to be maintained constantly on the flip flop inputs. That means, it is the time before the application of the input, that is why it is termed as setup time. Okay. So, propagation delay was input has been applied, input has entered the circuit, and now whatever time the circuit takes for processing is the propagation delay, but the setup time is the time before the application of the inputs. That means, which is saying that it is a minimum interval of time for the logic levels to be maintained constantly on the flip flop input. So, if I want to apply 1 to the input, then that 1 I cannot say that I have applied 1 and then removed it. That 1 has to be constantly there, and that amount of time for which that 1 has to be constantly there for that, so that it is reliably triggered, reliably fed to the flip flop on the edge of the clock. That means, this becomes the setup time. So, the complete definition is, it is the minimum interval required for the logic levels to be maintained constantly either low or high. Okay. So, constantly on the flip flop inputs prior to the triggering edge. So, before the triggering edge. Okay. It is also known to us that the flip flops are dependent on clocks. Without clocks, flip flops cannot operate. So, whenever the clock will be coming, and further we also know that the clocks flip flops are edge triggered. So, when these edges are going to come, so it should not happen that my flip flop input was applied and it got removed and the flip flop clock's edge is not yet arrived. So, if this is the case, that my input has been applied and it has been removed even before the clock edge is arriving, then that input might go not, it will go undetected. Okay. So, this is the setup time, that means for that much of amount of time input has to be there, so that whenever the clock edge arrives, then it will be triggered inside the flip flop, it will be fed inside the flip flop. So, this is the setup time. Okay. Now, hold time. So, as the name suggests, that means the value which has been applied, it has to be maintained there. Okay. So, the hold time is the minimum interval required for the logic levels to remain on the flip flop input after the triggering edge of the clock pulse. So, the setup time is the minimum amount of time before the application of the clock or before the arrivals of the clock edge. Okay. And this hold time is the amount of time required for which the input must be maintained at that level after the edge has arrived. So, the time before the clock edge is termed as setup time and time after the clock edge is termed as the hold time. So, both are having some minimum values. For that amount of time we have to maintain those inputs. Okay. So, that these inputs are reliably triggered inside the flip flop. Okay. So, these are the three characteristics. Now, let us proceed with the next thing, maximum clock frequency. So, maximum clock frequency, it is the highest rate that a flip flop can be reliably triggered. Highest rate, that means clock are the square wave pulses. Okay. So, the number of square wave pulses entering per second becomes the clock rate of that flip flop. So, if I am sending 10 pulses per second, the clock rate becomes 10 hertz, or we can say. Okay. But in terms of the advanced processors which we are using in our today's technology, these are in gigahertz. Okay. That means there will be 10 raised to power 6 pulses per second minimum of, sorry, not even 10 raised to power 6, it will be 10 raised to power 9. Okay. So, it is the highest rate that a flip flop can be reliably triggered. That means, the number of pulses that can enter the flip flop, now that much speed it can offer in the applications where the input changes are within those clock rate. Okay. That means, if my input is changing at the rate of 100 transitions per second, and if my clock rate is greater than 100, then all those inputs will be reliably triggered. Okay. But if clock rate is less and the input data rate is higher, then in that case some of the inputs the output obtained will be skipping some of the data points. Okay. Because the transition in the input side are greater than the edges observed in the clock. Okay. So, this becomes the maximum clock frequency, that it should be as maximum as possible, that is why it is shown as maximum clock frequency. Then the power dissipation. This power dissipation is the total power consumption of the device. So, whenever input is applied, the gates are there. These gates, in the fourth unit we will see that these gates are not just like these are the symbol of the gates which we are using. The inside structure of these gates are composed of resistors, transistors, diodes, etc. These are all our components, active or passive components. So, these active and passive components definitely will be consuming some kind of power. So, all the power consumed by those internal circuitry of the gates and the combination of these gates is termed as the power dissipation of the device. Okay. Then the next characteristic is the pulse width. So, the pulse width are the minimum pulse width specified by the manufacturer for the clock set and clear inputs. This set and clear inputs we are going to cover in the next slide, next topic. Okay. So, we will be defining these set and clear there, and what are the width for this clock, this has to be understood very clearly. So, pulse width is the minimum pulse width. So, if the width of the pulse is less than that, then again it is directly related to the pulse, means the time duration. Okay. So, if that pulse width is lesser, or we can say that, then it will directly impact the setup and hold time. So, that is why pulse widths are also important, although it is related to the setup and hold time. Okay. Then these were the characteristics of our flip flops. Now let's cover the flip flop with asynchronous inputs. So these asynchronous inputs, as I have already mentioned in the previous slide, that there are two asynchronous inputs, set and clear. So set is also known by the name preset. So these are preset and clear. Okay, preset and clear. Why it is known preset? That preset means already set. Okay, that means before the operation of the flip flop even starts, the output will be already 1, output will be already high. That's why it is mentioned as preset, pre high value. Okay, so these are asynchronous inputs. PR denotes the preset and CR denotes the clear. In some books, CR is also denoted by CLR. Okay, so both are active low inputs. By active low, this has to be very much, this is very important thing which has to be understood clearly. By active low we mean that the value which should be applied at the terminals of these inputs should be low to make them work. Generally, in all the cases, all the topics which we have covered till now, we have been using the active high terminology. That means whenever we supply the high input or whenever we provide the high input to a circuit, it starts operating. Okay, but these are the active low inputs. Active low input says as that to activate them we should be giving a low value. Okay, so what is the task which is going to be performed by these preset and clear inputs? If preset is activated, it will make the output. Sorry, preset makes the output high and clear makes the output 0, and this change will be permanent until these preset and clear are disabled. So if I have activated the preset, output is going to be 1 always until I disable the preset. Similarly, if I activate the clear, then output is going to be 0 always until I disable the clear. Okay, so these preset and clear, these are the task of these inputs, and these are located on the top and the bottom of the flip flops. These are just the terminology where in the logic symbol how to show these preset and clear locations. Okay, and in the circuit, these preset and clear are applied on the gates which are delivering the final Q and Q bar outputs. Okay, so preset and clear are actually marked here. Okay, so this becomes the preset and this becomes the clear. Okay, so these are the preset and clear inputs. So these are the actual location of the preset and clear inputs. Now let's understand the operation of the flip flop in conjunction with the preset and clear inputs. So in the first case, PR is 0, CR is 0. That means preset and clear both are activated. Both are 0, that means both are activated. Now preset wants the output to be high, clear wants the output to be low. So both are activated, both will fight with each other that I want to make the output high and I want to make the output low, which is practically not possible. So that's why whatever you apply at the input side, output will be invalid. Cross, we can say that, or it will be invalid. Similarly, for the next case 0 1, for 0 1 case, we can see that preset is activated and clear is 1, that means clear is disabled. So preset is activated, that means preset will make the output high. Preset will make the output high, and J and K, these inputs are irrelevant. That's why we have mentioned them as asynchronous inputs. Asynchronous means they are not dependent on anything. They are not working in synchronism with any other thing. Which are the other things which can be in synchronism are the flip flop inputs and the clock. So these preset and clear are independent of the flip flop input and independent of the applied clock. That means whenever they are activated, they are definitely going to make the output high and make the output low respectively, and they need not to worry about what is applied at the input side. Is the clock available? Is the clock not available? Because these two gates are independent of these inputs and clock. Okay, so that's why these preset and clear will take the control of the flip flops operation. Okay, So, similarly for the third case you can see that now clear is 0. Clear is 0 means that means clear is activated. Clear is activated, so the output will be 0. J and K inputs does not matter. Okay. Similarly, next case is J preset and clear are 1 1. So, for the flip flop to work actually, these preset and clear are going to be disabled. So, J K can have 4 values. So, I have placed 4 double 1 values of preset and clear. That means, for all these 4 cases preset and clear are not activated. So, if preset and clear are not activated, then my actual flip flop can work. Okay. So, in this way we can see that this is now the conventional JK's truth table. For 0 0 I will be getting a no change, for 0 1 I will be getting a 0, for 1 0 I will be getting a 1, for 1 1 I will be getting the QN bar. Okay. So, in this way these preset and clear inputs are controlling the flip flops behavior irrespective of the applied input and the clock. Okay. So, these are flip flops preset, flip flops asynchronous input, that is preset and clear. So, these are very much important topics which are, or we can say these are very much important concepts which we are going to use in our next lecture, in which we will be designing the asynchronous counters. Okay. So, in those counters these preset and clear, primarily clear, but preset can also be used. That thing we will take care of in the coming lectures. So, with this we come to the end of this topic. Now, let us start with the last topic, asynchronous and synchronous sequential circuits. So, it is well known to us, it is very much clear to us now that there are some sequential circuits in which there is a feedback, and feedback of the input for the next output generation is governed by the clock signals. So, if clock is the controlling factor for generation of the next output, this becomes the synchronous circuit, and if the circuit's next output is independent of the clock, then it becomes asynchronous circuits. It uses clocked flip flop, it uses unclocked flip flop. Unclocked flip flop, that means latches can be used. Okay. The state of the synchronous sequential circuit are always predictable and thus reliable. Why we are saying that the output is predictable? Because it is dependent on the clock. Whenever we are applying the clock, only then we will be getting the output. So, we can say that it is a reliable output. But in an asynchronous circuit, whenever you are changing the input, it will result a change in the output. So, I might not be able to detect all the output changes corresponding to the input changes, and when there are more than one input, then there might be a race between the two inputs that I will change the output first. So, if the output is changing from 0 0 to 1 1, then if 0 0 to 1 1, A and B are the two values which are going to change the output, then in that case there will be a race between A and B, that I will change the output first and B will say I will change the output first. This is not the desired situation. Okay. And the last thing is, this is having a simple design, and these are relatively complex designs, and this is a bit slower and this is faster because it is not waiting for the clock. Okay. So, this is the difference between the synchronous and asynchronous sequential circuits, and these are some applications which we are going to cover in our next lectures. Shift resistors, these are the different applications of shift resistor where they are used. Similarly, counters, sequence generators and pulse generators. So, our next lecture in which we will be covering these applications. So, with this we come to the end of our today's lecture. Thank you very much.